Hello everyone, my name is Mark Kaufeld, and in this presentation I will introduce our new work titled MP-RBFN, Learning-Based Vehicle Motion Primitives Using Radial Basis Function Networks. This research is joint work with Mattia Piccinini and Johannes Beetz from the Autonomous Vehicle Systems Lab at the Technical University of Munich. Motion planning for autonomous vehicles is commonly addressed using two main classes of methods. On the one hand, optimization-based planners can generate very smooth and dynamically feasible trajectories, but they are often non-convex and computationally expensive, especially in dynamic environments. On the other hand, incremental and sampling-based planners are fast and robust, but they typically rely on simplified vehicle models, which limits accuracy. This creates a fundamental trade-off between computational efficiency and precise representation of vehicle dynamics. Our idea is to bridge this gap using learned motion primitives. Instead of handcrafted or analytically derived primitives, we propose MP-RBFN, a framework that learns motion primitives directly from an optimal control problem. This allows us to retain the speed and robustness of incremental planners while achieving an exact representation of the vehicle dynamics as defined by the underlying optimal control formulation. Motion primitives have been studied extensively in the literature. Existing approaches include geometry-based primitives such as polynomials or clothoids, numerical optimization-based methods, analytic optimal control solutions, and learning-based approaches. However, we identify several key limitations. Many methods neglect vehicle dynamics. Others are computationally prohibitive. Analytic approaches often assume significant simplifications, such as linearized dynamics, and learning-based methods typically learn paths only, rather than full state trajectories. This motivates a method that can learn complete, dynamically consistent motion primitives efficiently. MP-RBFN consists of two main components. Offline, we first define a user-specified optimal control problem that captures the desired vehicle behavior and dynamics. By solving this OCP for a wide range of boundary conditions, we generate a large dataset of optimal trajectories. These trajectories are then used to train the radial basis function network, which learns to represent motion primitives in closed form. Online, MP-RBFN is used directly inside a sampling-based motion planner. At each planning step, the planner samples boundary conditions such as target positions, orientations, or velocities. For each sample, MP-RBFN predicts a full dynamically feasible trajectory in a single forward pass, orders of magnitude faster than solving the original OCP online. The resulting trajectories are then evaluated using a cost function, and the best primitive is selected for execution. In this way, MP-RBFN combines the optimality and dynamic consistency of optimization-based methods with the speed and robustness of incremental sampling-based planners. In this work, the motion primitives are generated from a minimum jerk optimal control problem using a nonlinear kinematic single-track vehicle model. The acceleration is thereby constrained by an elliptic GG diagram, and we heuristically limit the engine power to model changing driving resistances at higher velocities. Importantly, MP-RBFN is not tied to a specific OCP formulation. Any optimal control problem used for trajectory optimization can serve as a training source. This makes this framework highly flexible and extensible. The core of our approach is an extended radial basis function network. It includes radial basis functions as activation functions, an additional latent space which proved crucial for convergence, and a linear interpolation branch that explicitly enforces initial and final state constraints. The full model contains approximately 165,000 parameters. Without the latent space extension, training did not converge reliably. We generate a large dataset using a BMW 320 vehicle model with a planning horizon of 3 seconds. Initial velocity and steering angle are sampled across a wide range, covering many vehicle states up to 100 km per hour. Final states are determined by feasible acceleration and deceleration limits encompassing turns of up to 90 degrees. In total, the dataset contains 2.6 million kinematically feasible motion primitives, providing dense coverage of the state space. With this dataset, the network is trained for 2000 epochs using a weighted mean squared error loss over all state variables. We evaluate three different radial basis functions: Gaussian, inverse quadratic, and inverse multiquadratic. Among them, the Gaussian RBF achieves the lowest prediction error and is used in the final model. We compare MP-RBFN against analytic motion primitives, standard multilayer perceptrons, and direct OCP solutions. MP-RBFN achieves significantly lower trajectory error than analytic motion primitives and MLPs, and inference times within milliseconds on CPU. On GPU, significantly faster inference times can be achieved, but are not stated here because they are not comparable with the CPU-based analytic approach. This enables the generation of thousands of motion primitives in real time, making the approach suitable for sampling-based planners. As an example, we integrate MP-RBFN into a simple motion planner, where it is used to efficiently grow trees of dynamically feasible trajectories. The two illustrative examples show the successful usage of MP-RBFN to plan overtaking and turning maneuvers. This demonstrates that learned motion primitives can be directly deployed in realistic planning pipelines without sacrificing performance or feasibility. Now, we are reaching the end of today's presentation. To summarize, MP-RBFN is a framework for learning motion primitives optimized by arbitrary optimal control problems through radial basis function networks. It combines high accuracy, extremely low inference times, and strong flexibility. Future work includes the training on more complex vehicle models and validation on real test vehicles. Since MP-RBFN is differentiable by design, we also plan the integration into a differentiable prediction planning control stack for end-to-end optimization. The key takeaway is that MP-RBFN enables efficient, accurate, and flexible motion primitive generation, making it a strong candidate for next-generation autonomous driving planners. As we conclude the presentation, I'd like to thank all of you for your attention. And for those of you who are interested in exploring more details, we have provided QR codes which directly link to the paper, the GitHub repository of MP-RBFN, and our lab website for more information about ongoing research projects. We are excited to share our work with the community and welcome any collaborations or discussions. Once again, thank you for joining the presentation of the Autonomous Vehicle Systems Lab today.